Hi, my name is Alan, and this is work done at Heriot-Watt University with Ron Petrick, and it's called Incremental Domain Model Acquisition with a Human in the Loop. It's in domain model acquisition, so you've got a problem domain. You hopefully have some observations from the domain, and you want to create a model so that you can use it for planning. In this case, we're at least partially interested in observations that have noise or are missing values. So the specific scenario we're interested here is you've got some kind of supervisor, and they're going to be checking your plans and potentially have to create plans themselves if you can't create one, right? So we're in a scenario where you're building information, the system's building information during its interactions with the expert. It's producing plans, it's getting feedback on the plans. Okay. So the approach is based on Locum, so we're going to have an overview of some of the Locum structures. So the first part of the analysis is creating kind of transition pairs. The first analysis looks at objects, and it looks at which transitions, which is a kind of action with its argument number, can follow which other actions. So this box 1 has first a load and then an unload, and this means that our model will allow this kind of structure, and potentially further on the plan we'd have another load, and we'd complete the circle. Okay. There are also state parameters, and basically they're just capturing, for example, if you load a box into a truck, you know that you're going to unload the box from the same truck, right? So there's an analysis to find that kind of constraint. So this is looking at what happens if you add the noise. So this is just one change from box 1 to box 2, and in this case, because you've now got box 1 and then box 1 in 2 loads, you add this, and this unload might also come from box 2 and what it's doing elsewhere. You get problems in your state parameters, and in general this is the transition matrix for transportation domain, and this is what happens after this. This is quite high noise, but you're losing this kind of information here. So we're suggesting this incremental domain model acquisition framework. So you've got the expert and the system, and so the system starts with no knowledge about the domain, and the idea is, given it whatever knowledge it has, it's going to make a model and use that model to make a plan for some scenario that the expert is going to provide. And then whatever happens to that plan, we'll talk about in a second, it's going to update its knowledge base, and then it's going to start making a new model for the next iteration. Okay. And the idea is that this knowledge is going to grow over as the number of episodes increases. Okay, so the expert is going to provide, these are actual just the problems that they want to solve, and they're going to look at the plan generated by the system, and they're going to either tell them where it failed, or if it doesn't fail, then they can use the plan, and if it has failed, then they're going to create a plan, and the system can get a noisy version of that plan, right? So we're going to assume that their communication is not so good. Okay. So in terms of the partial knowledge, we're going to use the Locum structures to kind of maintain a partial knowledge. So in this case, we have our transition matrix. I'm not going to talk about the state parameters here. And we've got these 3 values that each pair can have, either unknown, maybe, or yes. And the idea is that if the expert, if their noisy plan has the transition pair, then we can label that as a maybe, right? Because we've seen it in a plan, but it might not be actually true. If it's unknown and we've never seen it, then we assume that it just cannot be So we assume at least eventually we will see every transition pair. And so we're not going to search through any of those, right? When the expert validates our plans, we're going to assume that this is accurate, right? So we've put a yes here and we've ticked it, and that means that we won't look at any models that don't have this transition pair. Okay. So in terms of the requirements for the expert's information, just to be a bit more specific, we're expecting accuracy in terms of applicable actions. Now this is to do with statics. So in Lockham, there's different ways of kind of getting statics inferred, and one is to use applicable actions, initial state, and their validation, and basically one thing that we're aiming for is to always be using action headers or yes no questions based on action headers, to ask them as much as possible, and I think everything is in terms of action headers. And then low accuracy, we can basically get example plans, and all that we expect is that eventually these will have all the action pairs, right? All the transition pairs, and all the state parameters, the things that we need to see. That's our only requirement on plans. And if they're very noisy, then it will take longer for the system, but that is the only requirement. So we've implemented a prototype and done some evaluation, and we're using gripper and logistics domains, which are both Lockham 1 domains. We've used 5 example scenarios, and we've given reachable actions, and we're using actions to describe the initial and goal states. In terms of the user or expert, we just select one of the episodes. We use a target model to validate the plans and indicate which action was the first failed action. And we've also got some kind of plan generation with parameterized, so that we can control quality and communication noise. And the kind of key measures we're interested in are the number of plans that the user must provide. Feedback with this is they're invalid plans, but the system generated a plan, but it wasn't okay. The number of plans that the user must provide, so that's in any case the planner didn't provide a good plan. The first episode that the system generates a valid plan, and the last episode a valid plan is not provided by the planner. Right? Okay, so this is just to give a kind of bound of when the user is actually going to have to pay attention. Okay, so in terms of the number of noisy plans required to cover all transition pairs, so this is the number of plans we need to see before we could actually potentially generate the target model given our assumptions. It's about 11 in gripper and 8 in logistics, so this is quite a few. And once we've seen enough, what is the search effort required to find the target model? Okay, so if we look here in terms of gripper, we've got 33 potential candidate pairs, right? So these are maybes, and they're all fair game. They're all could be valid. So the space of potential models is quite big even for gripper, right? So we've got this number of nodes that we looked through. So we ordered these by the number of times we'd seen them. So if you've seen a transition pair hit many times, then you can hopefully have more confidence that it's an actual hit rather than noise. But it's a heuristic, obviously. We saw 12 unique Lockham 1 transition matrices. So this is an interesting point, which becomes interesting more in logistics, is that a lot of transition matrices just aren't kind of representable in Lockham 1 models. So actually our search is kind of in this transition matrix space, which is wasting a lot of effort. which becomes more obvious. So in logistics, the space is 113 potential candidate pairs, and we needed to search through 50,000 transition matrices before we found even our second unique Locum 1 model, and this it just became a ridiculous space. So we need to actually implement a search in Locum 1 model spaces. So anyway, focusing on Gripper, and in terms of user provided feedback, they only had to provide feedback on just over three plans, which is promising. They had to provide 16 plans, and the system generated its first plan after 8 or 9 episodes, and their last failure after 18 or 19, and there was one kind of rogue run, which has made these numbers worse than they actually were. It was typically what happened in all the others was that you saw they generated a valid plan, and then a few later they never create another error plan, right? But there's something going on. So in conclusion and future work, we've presented an incremental approach to domain model acquisition. The system maintains a partial knowledge which builds through a series of episodes. This partial knowledge is defined using Locum-inspired structures. We have defined the role of a supervisor, which is a fundamental role in the framework. The system searches for a model that is consistent with its partial knowledge, and our kind of future work is to perform a full evaluation of the approach, to incorporate model-light approach to planning, and that's basically to get more information earlier, so to get rid of some of these maybes if we can, and try alternative model learning approaches within the framework. Okay, thanks very much.